don't go through and say what all this means really, but last time I went through a bunch of dynamic programming equations, and the most mysterious one, am I on?
Yes.
The most mysterious one was this average cost optimality equation. But you know, I had not intended to explain any of these dynamic programming equations. I was going to wait, and I don't know why I didn't wait. So the next lecture I'll go through and more carefully explain their origins. So this is this mysterious fixed point equation in this H star, which is a relative value function. So all right, so you solve this equation, you know, it's a fixed point equation of function h, and this is a meaningless quantity pretty much. Nobody gives a damn about it. But the minimizer gives you the optimal policy. All right, that's the thing. And if you plug in the optimal policy, you know, if you look at the resulting transition matrix with this policy, this is nothing but Poisson's equation. So that's why I made such a big deal about Poisson's equation. Then there was also, so in an example, you know, then this, just to get rid of the mystery, what I mean by PU H of X is nothing but taking the expectation of H of the right-hand side, right? But I'm just saying xt is x and ut is u. So it all becomes deterministic. Right, so when I have it take a function h and I hit it by pu, I'm doing exactly the same things I did before. Right. Now the reason I bring in this particular guy is that, you know, that associated with this difference equation is a ODE. Remember that, you know, and so remember H star again. You have a representation, but it's not something you'd care much about. For an ODE, you might look at the total cost. And so it satisfies a very, very similar equation. I regret it now. If I'd put the H star on the left-hand side, I would have gotten a generator, you know. But it's because I've got a generator here. Right, so I'm going to write, like, du would be pu minus I. So if I brought this over here to the other side, I'd have a generator and H star. And here it's a generator, meaning I'm differentiating in some way. So it's just like we had, the F stands for fluid model or OD model. So this df for any function h at x. Oh, that's right, I should put the top, sorry. I need a u, so I'll put the f on the top. So it's what's the derivative with respect to time of h of little xt, evaluate t equals 0, when x0 equals x, right? So instead of taking differences, I'm taking derivatives. But by the chain rule, I take the gradient of h at x, and I dot that with x dot, but x dot is f bar. So we've seen all this a few times. All right. And so last time I justified how you could maybe connect these guys together. So last time, I can replace du with a fluid by du here. All right, so that's where we ended at the last lecture. I basically went through and I stuck in J star here instead of H, and I went through and did a Taylor series expansion. You know, I took this expression here, I plugged in H equals J star, and I did a Taylor series expansion around X. All right, and so when I did that, I ended up getting an expectation of F, which gave me my F bar. So go back to your notes. You do a Taylor series expansion of this, and you get that. Now, this approximation is pretty crude because smooth, what do I mean? I mean, it's not, the error, what I'm really hoping for is that this is small compared to C. That's what I'm really curious. You know, maybe it's bounded. Like by being approximately 0, maybe I mean just a constant. You know, because these cost functions are going to blow up. You know, so anything that's bounded, I'll be really happy if it's bounded. You know, and go back and look at inverse dynamic programming. This is what I call the Bellman error. Okay, and if the Bellman error is small in some sense, all I care about is this thing being small relative to C, and I've basically solved the problem. Because basically, whatever this minimum is, right, I can just subtract it from C. I've solved the dp equation for a different cost function. You know, and if the Bellman error is small, then the new thing I'm optimizing is very close to the old guy. I can't get the entire old lecture. We said a lot, you know, this, you know, this was a really important point, this idea of inverse dynamic programming. Well, I won't review it now. We'll come back to it. Okay, so how do we solve this baby? So this is motivation for trying to solve this. So we have this example. You know, it's just a boring Q again. But what's not boring is that there's a cost function which is non-standard. And in general, you could write down just an arbitrary function here, some function of how many packets you can process per time slot, and a parameter R, which is basically trying to give some trade-off between, you know, you really, it's a multi-objective problem. You'd like to keep your cost of processing low, and you'd like to keep your waiting time low. And so basically, we'd like to solve this for every R. so to understand the trade-offs, Maybe what we really care about is we'd like to minimize the mean of x subject to a constraint on this. And so we could vary r until the constraint on the mean cost satisfies the constraint. All right, because all problems are multi-objective. There's never really a single cost. All right, so basically we can solve this mother, except, let's take take it to be u squared. The problem, as I mentioned at the end of the lecture, is that this is then always infinity. So it's good this is a black cloud. Now, is that a smooth function? Maybe it is, but everything falls out. It's just, if you look at this, the fluid model, the mean of this, it's just x minus u plus the mean of that, which is alpha. And the point is that if you make x go to 0 and stays there, so if we're looking at this integral and want this to be finite, then surely we want this to be 0 eventually, or at least converge to 0. But if we get to 0, or if we converge to 0, then the derivative will converge to 0. And if that's the case, then x dot is 0, x is 0, you get u equals alpha. All right, and so my cost becomes 0 plus r times alpha squared, no good. All right. Okay, so you've got to change. Okay, so you got to change it. So you can't apply this directly. So what do you do? So approach 1. What's that? That's one thing to do. So there's two things you have to do. So approach 1 is to mimic the representation we had for the relative value function. I won't write it down again, but you could write it as an expectation of a sum up until reaching some state. So in the notes I call it k star of x. So that's a reasonable thing to do as well. Just look at the minimum over all input processes of the integral from 0 to the first time you hit the origin. Again, that's really well motivated. Basically that, and you don't care, you just stop. And how much, let's see, how much, yeah, we've got time. So the thing to do if you have a problem like this, you've got the HDB equations. You can go through and plug it in, and you get some big algebraic mess, and you don't get a lot of insight. But you can play around and get bounds, And for example, to get a bound, you can just make u constant, because we understand that perfectly. right? So I'm minimizing over all inputs. So what you can do is you could try a constant input and then minimize over mu and see what happens, right? Yeah. And do you remember what happens? That's the fundamental theorem of triangles. So if you take that constant input and you plug it in, there's x. Oh, there's no x there. Sorry. Yeah. Yeah. If you plug this in, so of course you're going to have to take mu large enough so you actually stabilize the system. So mu is going to be larger than alpha. And then we've done this before. You're just going through and integrate into the curve, and then you have what we've got this minus mu minus alpha is the slope, and so the time that you hit the origin is just the initial condition divided by that slope. And so then you can work it out. You can work out the cost. So the cost is, I'll just call it k of x. And so we've got xt, that's here, plus r times u squared. I shouldn't be using this. Is that clear enough? All right. So I didn't put the star here. So k star is the minimum for all inputs. So it's customary if somebody gives you an input, you want to evaluate it, you just get rid of the star. All right. And so we know what t0 is. I gave you a formula for it. For this one, it's just x over mu minus alpha, and for the x part, the integral of this curve, like I joke, it's the fundamental theorem of triangles. It's the area is 1/2 the base times the height. All right, so you get that. Oh my God! Oh, we're in trouble. Oh my God, we're in trouble.
We need bigger iPads.
No, I think that is one of these dry erase. They're both dry erase pens. Is that yours?
Looks like an erase.
Wow. What's this? We need. I think the erase. I'll be right back. You want to go look?
No.
Oh my God. Has anybody worked out what k is? No, I think it's bad. I think we have to throw that away. I think if you go down the hall, see if you can find somebody. Jesus. That's a great gag. It's not even April Fool's. Has anybody worked out what this is?
I just made one.
Oh, really?
I don't think it's going to.
No. But so the integral of the x part is the fundamental theorem of triangles. It's 1/2 the base times the height. So you get a 1. So the base is x over mu minus alpha, and the height is x. So you just get x squared. And then you get the other term here. It's just a constant. So it's r times u squared. So it's plus r times mu squared, because we're just taking ut to be mu, times the length, which is x over mu minus alpha. All right, so huh. You know, it's really kind of funny is that it never occurred to me before until just now that we could go now and optimize over mu, and the optimizer would depend on x. So first of all, we see that k, this is quadratic, so k is less than a quadratic. So we know that when we minimize over all u, we get something with quadratic, no more than quadratic growth. But I bet you anything, if we went through and took the derivative with respect to mu and set equal to 0, we get a mu star that would depend on x, and we'd actually get something close to the right answer, you know? It just occurred to me now. If we wouldn't get a quadratic, yeah, because we'd get as we make x larger, we would end up making mu larger somehow or something. We might even make mu the square root of x. Because you see, if you make mu the square root of x, then these two guys have the same size, sort of. Well, there's a mu there still, but maybe not. But you get a mu that blew up with x. So amazing, it never occurred to me until just now. I'm stalling for time because of this. Okay.
So you pick your mu based on the initial condition.
What's that? Well, yeah, that's right. But the thing is that that'll give you better bounds, but it won't solve the problem. So with this, it turns out that's not the right answer. It's not quadratic. It turns out you can go and it turns out, oh yeah, that's right. So this finite horizon problem has exact same dp equation as that. They're the same. It has a boundary condition that maybe the boundary conditions are different or something like that. But these solve the same ordinary differential equation. So you can go and actually solve this. And what you get is something ugly as hell. So 20 years ago, my students worked this out. Basically, I mean, beginner students in stochastic control did this, and you get alpha x, you get a linear term, and then you get something not quadratic, really. I love it. There it is. And if it's wrong, don't tell me. I don't care. But anyway, this is the first thing we tried. And you see that instead of a quadratic growth, you forget the 2x plus alpha squared. Forget that. For large x, this grows like x to the 3/2. So it's slower than quadratic. And so it makes me wonder if you minimize this over mu, would you get something like x to the 3/2? It'd be interesting. Again, I don't know why I didn't think of that. All right. So anyway, that's approach number one. Approach number two was proposed just here a moment ago. It's the center thing. So any hope? Thank you. Cross your fingers, everybody. No better. It's worse. It's much worse. Oh, we're in trouble. I wonder what happened. Yeah.
I think this is micro.
What's that?
Just use the
tissue?
Make it look like a.
Yeah. Oh, I see. But but I want to ruin your.
You can use it. It's all black. I don't care.
Let's try it out. No. Thank you very much, though. This is fun. Anyway, we'll see what happens. Yeah, actually, a wet towel maybe. Look at this. Oh,
I know someone.
I mean, really, whoever invented the whiteboard should be thrown in jail.
Whoever did this.
Jesus. Okay, so what was that? Oh, he's gone. But somebody blurted out the other approach. Is that The whole reason that this was infinity was because of this equilibrium condition, that u had to be alpha. So what you do in control courses is you look at deviations. You know, you never put a cost on u, you put a cost on u minus its steady state value. So that's, you know. Okay, what do you think? Oh my God. This will be completely ruined now.
You can't get it work. Well, it works.
It does work. We'll have to wait for it to dry off.
Right.
Oh, yeah, you got there recently. This is the last one I have.
Wow.
What?
Maybe
Whoa! This is great.
we'll try. Oh, no.
Oh my God, this optimization was done without dynamic programming. It was completely model-free.
Well, you also works better.
Yeah, just a little bit of exploration. And the thing is that now the whiteboard has been rendered completely worthless. Oh, no, it kind of works.
That's pretty good.
Yeah, thank you.
Well, I think like it should just get like we could make it dry.
Yeah, it does ruin the pen, but that's okay. All right.
There are notes.
Okay, cool. Yeah, there are notes. The notes here are really clean. So, but again, so this should have been our starting point, because again, when you have a nonlinear control system, as this is, it looks linear. It's nonlinear just because of the deterministic, this constant disturbance. You always look at the cost, the deviation from the equilibrium. And the equilibrium here is where x equals 0 and u equals alpha. So you should always have a cost from that. So that's a natural thing to do. Oh, thank you. All right. So let's, with this, things are pretty nice. So let's go back and look at J star with this.
Your use.
Yeah.
Oh.
It'll start working again. This is fun. We'll make this. What the hell happened? So just remember what this is. And let's write down the HDB equation. So we've got our F bar, which is minus u plus alpha. Dotted with gradient, which is just the derivative. And that is just x minus, x plus r times u minus alpha squared. All right? And I bet we can solve this calculus problem. Now, the problem is, of course, it's u greater equal to 0. We're only allowed to, I didn't say that maybe, but I said it last time. We're not allowed to, to suddenly create negative work. But we can hope for an interior optimizer. All right? Again, hope. So you basically say, either it's 0, either it's a boundary optimizer, or it's a interior optimizer. Everything's falling apart? No? Okay.
It's recording.
And so take the derivative with respect to, So take the derivative with respect to u star. I've got this. I've got 2r times u minus alpha. That's the derivative of that part with respect to u. And then the derivative of this respect to u is just the minus grad j star. Except, yeah, that's right. And then I go through and do what? I solve for it. I get that u star is nothing but, I have to put it 1/2r. Well, first of all, I've got an alpha. So this is equal to 0. So I put a grad j star on the other side, I add alpha. Okay, now j star, you can guess it's got to look like this, right? It's obviously monotone. It's non-negative. You know it's increasing. I mean, look at the definition. If you're further away, it costs more to get to the origin, right? So you can guess j star is monotone, and so its derivative is positive. I know, or greater equal to 0 at least. I mean, who knows? I mean, it's hard to imagine its slope could be 0. So just basically, separately you could prove convexity actually. It's not hard to do. And because it's convex, it has to have a positive derivative, which means that's feasible. That's positive, that's equal to 0, it's positive. And so we hoped, our hope was right. So sometimes optimism is good. All right? And then you can look at u x star dot, which is over there. And you see that the alphas cancel, and you're left with that. And in the handout I say, isn't that beautiful? So the optimal input results in the state being gradient descent on the cost, which I think that is so pretty. And you always get that when you have this quadratic cost. It's just from that. All right. All right, so we haven't solved it yet, but what you do now is you take that form and you plug it back in. And that's the ugly part, right? So you go through now and you plug this in. So we've got, this is equation 1, say, and that's equation 2. And you have to take that and plug it in there and say that's 0. So I get rid of the minimum and I just plug it in. So I have x plus r, and I've got u minus alpha. So u minus alpha is just that. Quantity squared. All right. And then again, I've got the same thing. I've got a u minus alpha there, a minus u plus alpha there. So the same thing. Minus u plus alpha is just minus this. All right. All right, I have u minus alpha is that. And so minus u minus alpha is minus that. And so I've just written that down, dotted with that. And, you know, that is sad, isn't it? So what do you get? You get, did I lose something? Oh, this is squared. There's no r there. Anyway, let's just write it down. So is that really right? So you get, here I get a 1/4 and then a 1 over r. And here I have a 1/2 and a 1 over r. So it's minus 1/4. So it's x minus 1 over 4r times grad j star of x squared. All right. Now that's not that bad, right? Now at first thought you'd say, Jesus, this is a nonlinear ordinary differential equation, but it's just a difference. So I can take the x to the other side take square roots of both sides, and I have the grad of J star is just, square, let's write it down. I'm scared. Shall I dare? Well, I'll do this here so it can dry off. And somebody didn't do their work over here. Man. So what's the answer? What's grad J star? Somebody shout it out. I can't hear you. How come you're mumbling? Equals
2 square root of R2.
So I go plus or minus to be really formal and careful, but we know it's not going to be going downhill. Separately, you can prove convexity, and therefore it's plus. Okay, and that was our policy, right? We know that U star is just alpha plus that thing. It's equal to alpha plus this divided by 2r. This divided by 2r. So it's the 2's cancel, one of it's square root of r.